All right, now we're going to go ahead and look at aquatorts and aquifers. So aquatorts are impermeable layers that hinder or prevent any water movement. Clay is a very good example of what an aquatort is. As I said in the last slide, clay, although has a high porosity, has a very low permeability, and so it becomes a very good layer to prevent any flow of water through it. Permeable rock strata or sediment that transmits groundwater freely is called an aquifer. So sands and gravels are common examples of aquifers or areas that are permeable or rocks that are permeable and that can transmit groundwater freely through them and can store them freely as well. So if an aquifer lies between two aquatorts, then it is called a confined aquifer. When it is not bound by any aquatorts, or when it only has one aquatort on the bottom of it, it is called an unconfined aquifer. Okay? I should also mention, and I don't think I said it in the slide, that in an aquifer, typically you find groundwater. It's not just a simple rock strata where groundwater could flow through, but usually it's also a reservoir of water, or that's how we use it typically in geology. So how does groundwater actually move? Its movement is really not very easy to visualize because, again, it lies underground and we have no way to see it. And again, as I told you thus far in the lecture, it is a very slow process that water needs in order to get through from pore to pore or in between the fractured pathways. So the image here on the lower left shows a pretty simple groundwater flow system. It's a system in which you see a 3D body of earth material that has been saturated with moving water. So all of the things that appear, or the matrix of the rock that appears blue, is where groundwater lays, and then the area above, where it appears kind of beige, is areas where groundwater is not present. So the image shows the groundwater moving along flow paths from recharge areas. So this recharge areas is where the groundwater gets replenished, and then flowing towards discharge areas, which are areas along streams typically where the groundwater flows back to the surface. So again, recharge areas, typically topographic highs, water gets replenished, the water table is also a little higher, and then the water flows through and goes on to discharge areas, which typically are lakes or streams. Discharge areas can also be things like springs, and again, wetlands, for example. And in coastal areas, as the groundwater seeps, will become places like bays or even just the ocean as the groundwater seeps through. So groundwater movement requires a lot of energy, and this energy is typically provided by gravity. So water at depth will also move downward, not just at the surface. So water will move from areas of high water table to areas of low water table by the aid of gravity. Sometimes this movement is straightforward, so it will go directly from high to low point, but most often the water actually takes this kind of curve-like pathways, as you're seeing in the image on the bottom here, in order to get to the discharge areas. Sometimes the curved pathways even go against the force of gravity, as you're seeing over here once it gets closer to the discharge areas. So this happens because the deeper you go into the zone of saturation, the greater the water pressure that will be present. So again, the deeper you go, the greater the pressure. And so the water is going to be basically driven upwards due to this pressure. And so these curves form as a compromise basically between the force of gravity pulling the water down and then the tendency of water to flow back towards zones of lower pressures. So our modern understanding of the groundwater movement was actually founded on the mid-19th century by the work of a French scientist and engineer called Henry Darcy. So Darcy made a bunch of experiments, and one of them was showed by the velocity of groundwater flow, and he showed that it was proportional to the slope of the water table. So the steeper the slope on the water table, the faster that the water will move, according to Darcy's experiments, and which later seemed to be true. So when you have a steep slope in your water table, there will be a greater pressure difference between 2 points. So the water slope is known as the hydraulic gradient, and it's expressed as the change in head over a given distance, as you're seeing here at the bottom. The change in head itself is the elevation of 1 point on the water table minus the elevation of a second point of the water table, as this graph up here is kind of showing. So if you're trying to calculate the hydraulic gradient between this location and this location, the elevation at which H1 lies, or rather the elevation for the water table at H1 minus the elevation of the water table at H2 over the distance between those two measurements is going to give you the hydraulic gradient. So Darcy also made experiments with different materials. He did this by measuring the rate of flow inside tubes filled with these materials based in sediments, and then tilted the tubes at certain angles to check for the rate of flow. So by doing this, he found that the flow velocity varied with the permeability of the sediment. So he found that water flow is faster for sediments that have a greater permeability rather than those sediments that have a lower permeability. And this factor, Darcy named the hydraulic conductivity. And it takes into account the material's permeability and the viscosity of the fluid. So lastly, Darcy, amongst his experiments, he created the following equation that you're seeing there. This equation was made in order to find the discharge, which is the actual volume of water that flows through an aquifer in a specific amount of time. So in this formula, Q is the discharge, K is the hydraulic conductivity, so again the ability of the fluid or the material to transmit the fluid, which has a specific viscosity. A, which is going to be the cross-sectional area of the aquifer, or in this case for his experiment of the tube. H1, as I said before, was going to be the elevation at whichever point you are measuring the aquifer from. H2 is going to be the second point that you want to locate, and then all of that is divided by the distance in between those 2 points. Or in another way of saying that is discharge is equal to the hydraulic conductivity times the cross-sectional area times the hydraulic gradient. So this equation is also termed Darcy's law. And now if you know the area, the permeability, and the hydraulic gradient of an aquifer, you can easily calculate the discharge from that aquifer. So the total volume of water that flows through that aquifer on a specific amount of time, which is pretty awesome. So again, the image on the right here shows one of Darcy's experiments set up, and it shows you how he filled the tube with sediment of different materials. He poured the water through one of these tubes, tilted the tube at specific angles for which he calculated gradient, and then waited a certain amount of time until all of the fluid or certain parts of the fluid were discharged to his collection bucket, basically. All right. Now, knowing a little bit more about how groundwater moves, let's go ahead and look at wells and artesian systems. So, according to the National Groundwater Association, there are about 16 million water wells for all purposes in the U.S. 16 million. Out of those 16, 13 million are privately owned by households, and about 500,000 new residential wells are drilled each year. So it's a fairly increase or a high increase in the wells that are being drilled every year. So it is also estimated that in the US, about 50% of the drinking water actually comes from groundwater, whether it be provided by public supply or by private owners. So a well is going to be a hole that is bored into the zone of saturation and through which the groundwater is pumped. In order to ensure that a well has a continuous supply of water throughout the year, when again sometimes there will be drier times and the water table is going to be lower, the well has to penetrate below the water table at those dry times. So when you drill a well, you have to calculate, or you have to at least be aware of the level of water table during dry times and penetrate that well lower than that level of water table. So when we pump water out of the wells, we are typically lowering the water table around the well area. This effect is called drawdown. And this drawdown will decrease with increasing distance. So overall, this is going to result in a depression of the water table near the well, as you're seeing in this case. So you're seeing when we are collecting the water, when we're pumping the water down, we are causing drawdown, and as that drawdown increases, there is a lowering of the water table that decreases in terms of lowering, that while you increase further distance from the well itself. So again, that phenomena is called the cone of depression. Not to be confused with the cone of depression that dogs have, who look so sad. And that is shown again on that picture on the top part of the slide. So typically the cone of depression is negligible if the well is being used for household uses, but if there is continuous pumping being done for irrigation, for example, or for industrial purposes, sometimes the cone of depression can be quite steep. So it's going to become something like the one you're seeing in the picture. And it can also become quite wide as well. This widening and deepening of the cone of depression may actually substantially alter the water table in the area and can cause nearby shallow wells to become dry, as is the example here. So before the irrigation took place, all of the wells could reach the water table. After the high efficiency well started cranking water out for irrigation purposes, these two nearby wells dried out because they can no longer reach the new level of the water table. Sometimes the water table level may change dramatically across short distances. For example, if you have a private well and drill this well to about 50 feet, you may be able to pump water out. However, your neighbor, who, for example, also has her own well, will drill about 100 feet and not be able to pump any water out. So this phenomena can happen when there is a perched table or perched water table, excuse me, as is the example in the image over here. So a perched water table forms when an aquitard is situated above the main water table, like it is in the image here. So an aquitard lies here above the main water table, and whatever groundwater flows through the unsaturated zone and gets accumulated on top of that aquitard will be a local water table. So in this situation, you would be the owner of the perched water table aquifer, and then your neighbor would be this guy over here. This situation can also happen when your aquifer is made up from igneous, metamorphic, or some types of crystalline sedimentary rocks. These rocks don't have as many voids, and so any flow of water will be through fractures within the rock. So if your well does not actually intersect a fractured network from that crystalline rock, then it is likely that you won't be able to pump any water out while your neighbor that does fracture through, or the well does fracture through the fractured network, can pump the water out.